Hello everyone, welcome back to another past paper review. Today we're reviewing the CAPE physics paper. This is a unit 1 paper and is a paper 2 from the year 2016. Now let's jump into the first question. The first question reads, define the term acceleration and state its units. And so let's quickly define acceleration. And so this is the rate at which velocity changes. So the rate at which velocity changes, or you could define it as the change in velocity over time. All right, or you can say the rate of change of velocity generally, or simply the change of velocity divided by time. Now the units for acceleration, I'm going to write it in two ways, which is meters per second squared. So meters per second squared. Or you could write it as this, which is the same thing. All right, so those are the units. You can write either one of them. All right, so let's go to part 2. Part 2 reads that state Newton's second law of motion in words and the associated equation. So in simple terms, the second law states that the rate of change of momentum is directly proportional to the applied force. Let's put that one in real quick. All right, so again, it reads that the rate of change of momentum is directly proportional to the applied force. Or you could state it as this as well. Let's give you a different version of it, which means the same thing. And in this one, they say that the acceleration, so I'm going to state this in terms of acceleration. So the acceleration of an object is directly proportional and in the direction All right, so next way to state this is that the acceleration of an object is directly proportional and in the same direction of the applied unbalanced force. So that's very important as well. In terms of the equation, and this is where force, so F force is equal to mass times acceleration. All right, so let's go to the next part of the question. The next part of the question reads that, with this part B, it states that a car is traveling along a level road at a speed of 15 meters per second towards a set of traffic lights. When the light turns red, in 0.5 seconds after you've seen the light, the driver applies the brakes and brings the car to a stop at this traffic light. Table 1 shows the speed of the car the speed of the car changes from the time the driver sees the traffic lights turn red. All right, so now let's go through this. And so we have a data table right here, time and speed in meters per second. And so the first part reads that on the grid provided in figure 1, which is page 7, plot a graph of speed against time. So once you say a graph speed against time, you know that time will be on your x-axis. So let's go to the grid and answer or draw a matter of fact the graph. So the graph is already drawn. So let's go to that real quick to show you how the graph will look. All right, just to point out a few things, you must label your axis. Again, it is speed against time, so speed is on the y-axis and time will be on the x-axis. You also need to provide a scale to indicate exactly what you are measuring on your scale. All right, so have the scale for the x and y-axis. All right, so here on the x-axis, you'll have 4 centimeters equal to 1 second. And on the y-axis, you'll have here 1 centimeter equals to 1 meter per second. All right, so just to make sure you put your scales, make sure you label your axis properly with the units as well. And so if you notice this graph, how it comes right down, it start here first with the same speed, then uniformly decline. And I also draw a line of best fit. That is also important as well. Make sure you use a ruler to get a straight and a fine line, straight and fine line. Your points should also be fine as well, and you want to circle around the points. All right, so please make sure you make a note of that. All right, so what I want to go to now is the questions. So let's quickly answer the questions. So here now is to suggest the reason why the velocity remains unchanged for the first 0.5 seconds after the light turns red. And if you even notice on the chart right here, you'll see that when the time was 0, the speed was 15 meters per second, and also at 0.5, the speed is the same. So they're asking why the speed at this point remains unchanged. So let's talk about the possibility. Now, remember, the person will see the light, right? And then applies the brake. And so remember, even this question state that the brake was applied at 0.5 seconds after seeing the light. So why there's no change between 0 time and 0.5 is simply because here the time in seeing the light or traffic light so this time in seeing traffic light and applying the brakes, I could say it took 0.5 seconds. So there is a reaction time in terms of seeing the light then reacting to it. So the reaction time of the driver will take 0.5 seconds. So the reaction time is actually 0.5 seconds. Seeing the light versus actually pressing the brake. Okay, so let's just make a note right here. So the reaction time of the driver is within that 0.5 second, is within 0.5 seconds. All right, so just to make a note of that. All right, so part 3 is that what feature of the graph shows the car's acceleration was uniform. So what about the graph that shows that the car's deceleration, no matter of fact, was uniform? So what indicates a uniform deceleration? So let's just quickly go to that. No, go back to the graph and let's look at it real quick. And so if you notice here, this line is a straight line. Again, use a ruler to make sure line is really straight and neat. So it's a straight line going all the way down. All right, and so let's just apply that to the question. So let's put it right here. So I'm going to state it like this, some other fact, that the descending straight line. So the graph shows a descending straight line. So the graph is a descending straight line. All right, so great. So the fact that it's a straight line and it's descending, it shows you uniform deceleration. Let's go to part 4. It's a use your graph to determine the distance that the car traveled after the lights turn red to when the car stops. All right, so you're gonna let's just go back to the graph. I'm gonna show you the graph. So this graph is a velocity time graph, and so distance will be the area below the graph, and so you can find the area under this shape. I must draw two shapes right there. So this will go all the way down to 0. I just want to do it really rough. And so the height here is 15. So now this is 15. So it's going to be base times height. So this section is going to be base times height. Motherfucker should use lower cases. So let's say B times H. On this side is the triangular side. It's going to be half the base times the height. So half base times height. All right, so what I want to point out, because this first section here is from 0 to 0.5. So no, that definitely this is 0.5. And then 0.5, it will go all the way to, let me just go back down to the bottom of the graph. So you're going to see exactly what I'm indicating here. All right, excellent. So this will come all the way here to 0.5. And then the base of this is 0.5. Let's put 0.5 right here. All the way to 3.5. So let's now work this out. So the base is 0.5. The height is 15. On this section here, the base starts at 0.5 and ends at 3.5. So the entire base here is actually 3. Okay. So you can say this section is equal to 3, all right, times 15. And we can say this is, which is half the base, as you're going to say half 3. Okay, so half 3 times 15. And then the base here, it is 0.5, 0.5 times 15. Let's go back to the question and put the answer there. All right, so let's go to the section there. All right, so remember the rectangular part is 0.5. So I'm going to say 0.5 multiplied by 15. And that will equal to 7.5. And we'll add this to the second part, which is the triangular part. And it's going to be half base times height. It's going to be half of 3 multiplied by 15. And so going to be 1.5 multiplied by 15, which equals to, here it is going to be 22.5. All right, so just to make a note of that. Or you could say or you could say actually 3 multiplied by 15 divided by 2. It still works out. And so the distance here that traveled will be 7.5. Add that to 22.5. And that will equals to 30 meters. All right, so that will be a distance traveled based on the graph. Let's go to the next part of the question. All right, so let's skip over the graph, which is actually question number 2. And in question number 2, right, it said that a transverse progressive wave travels along a stretch string from left to right. The shape of part of the string at a particular instant is shown in figure 2. The frequency is 15 hertz. All right, before even going to question, you also remember that frequency is equal to 1 over t, right? So t is also equal to 1 over frequency. So just to point this out real quick, I'm not sure if this is necessary, but for this question, but t is also equal to 1 over f, which is 1 over 15, just in case you may need that. All right, so 1 over 15. All right, and so period, if you divide 1 divided by 15, you'll get 0.07. But let's see if this is needed any at all. So if it's not needed, then that is also fine. But just in case you may need to work this out on any given paper, you could do that. All right, so let's scroll down to see what's going on here. So in the first part of the question, you said use figure 2 to determine for the wave its amplitude. All right, so now we want to look at what amplitude is, and we're going to look at the graph carefully and say the amplitude will be the height of a crest or the depth of a trough. And so I could look at any one of them, and so this stops right here. Now, you need to know, so the height is from the 0 point all the way up to this point. All right, so go across. So what you need to know first and foremost, right, is the value of each of these points before you actually determine what that point is. So if this is 2, and so we think about 5 points or 5 lines between here, and this is 2, so you can simply divide 2 by 5. And if you divide 2 by 5, what you get is 0.4. So each single line is 0.4. So to calculate this, again, you get 7 here, and then this will be 7.6. So this is the 4th line, so this is 7.6. So our amplitude is 7.6. You can also do it from the trough as well. So this is 7.6, and the unit here, let's go back to the unit. So 7.6. Let's check the unit. So the unit that is measured in, it is millimeters. So 7.6 mm. All right, so great. Now the next part of the question is part 2 of this section here. It reads that phase difference between point P and Q. So we determine the phase difference between point P and point Q. All right, so let's go back to the graph. All right, so the phase difference here between P and Q. All right, let's just take this piece out to make it clear to see what I'm going to do right here. All right, so looking at the graph here in terms of the phase between P and Q. All right, and so here now, we should look at this carefully. All right, this is that the point is that phase right there, and this is here. All right, so notice there are opposite points. One is going up, one is coming down. And this is pretty much half of a wave cycle. Okay, but what is important here, right, is that this point will be 90. So this will be, let's just put the values here. So this will be 0. All right, on the wave, this will be 90. So this point will be 90. So this will be 90 point right here. And then it will come back down here, which would be 180. So here will be 180. And then after 180, go to 270. So this will be 270 right here. All right. And after 270, it will be 360 degrees. Now, what I want to point out right here, I'm just giving all the angles in terms of angles. Remember, the phase could also be measured in radians. But I want to also point out that a complete wave cycle is equal to 360 degrees. All right? Also, a wavelength is also 360 degrees. Just to make a note of that. So the phase difference will be 90, where P is 90, all right, and Q is 270. So we'll subtract 90 from 270 to give us our phase difference. And remember what a phase is. A phase could be a complete, the complete cycle, or it could be the wavelength, which is 360 degrees as a complete cycle, which means the wave actually make a 360 in terms of degrees turning, a 360 degrees turn. Okay, so but if you want to define what a phase is pretty much the angle measured in degrees, or the position of a point in a given time. Okay, so just to make a note of that. All right, let's just quickly go back. Let me go back to the question. I'm going down. Let's go down. And so here now the phase difference, I'm going to do it in calculation. It's going to be 270 minus 90. So 270 degrees minus 90 degrees. Okay, and that will give us our 180 degrees. So it's 180 degrees. All right, so great. So that will be answered right there, 180 degrees. All right, so now let's go to the next question. Let's talk about speed. So we're going to determine speed right here. And so what I wanted to note about speed is that speed is equal to frequency times wavelength. So we can say speed is equal to frequency times wavelength. Is equal to the frequency multiplied by wavelength. All right, so how we're going to work this out now real quick. The frequency was given in the question. All right, so the frequency was given in the question, which is 15 hertz. But now we need to determine what is the wavelength. And the wavelength, it is the distance between two equal points or two consecutive points on the wave. And so from point P, for example, all the way over to this point, let's just make a marking right here. So from P all the way over to the other crest, the top of the other crest right here, right, which is from 20 to 100, it is 80, so that distance is 80. Okay, and remember this was in centimeters, right? But what you need to do is to keep your units the same, because displacement was in millimeters here. All right, and so what I'm going to do is to change my centimeters into meters, okay? Because remember now it also measures in meters, right? Because speed going to be meters per second, not centimeters per second. So I'm going to change the centimeters into meters. And so if I divide 80 by 100, so remember now the distance between the two consecutive points is 80 centimeters, but I'm going to convert 80 centimeters into meters. So what I'll do first is to divide 80 by 100. So 80 divided by 100 equals to 0.8. And so that is my wavelength. And the frequency that was given, it is 15 hertz. So I'm going to say now that the speed is equal to 15 multiplied by 0.8. And that will give us 12 meters per second. That's equal to 12 meters per second. All right, let's go to the next part of the question here. All right, and the next part of the question is part B. All right, so part B now reads that another stretch string is used from a stationary wave. Is a part of this wave at a particular instant is shown in figure 3. The points on the string are at their maximum displacement. All right, so that's very important here to talk about maximum displacement. All right, because I'm going to point out something with that. All right, so here now it said state the phase difference in the motion of the points on the string labeled X and Y. So what I want to point out where X and Y is concerned is X and Y, they are pretty much in phase. And if they are in phase, which are on the same exact, well, not same exact point, but because one is going up, one is coming down. But based on where they're positioned on the motion of the wave, they are in phase. And if they're in phase at this point, then they're going to be equal to 0. So here, the difference will be 0 because they are in phase. Okay, so the answer here is going to be 0 degrees. Okay, let's put that in. All right, so 0 degrees. All right, and again, the reason for that is because they are in phase. Because they are in phase. All right. All right, so very important to note that. All right, so let's go to part 2 of this section. And it said distinguish between the term antinode and node when used to describe stationary waves on a string. All right, so let's talk about now what is the antinode and what is the node. Matter of fact, what I will also do is to kind of draw a diagram to actually to see this. But let's just distinguish between them real quick, and then we go into it. So when you talk about antinode, you're talking about the maximum point, okay, or the maximum displacement. So antinode, all right, is the maximum displacement or the maximum displacement or maximum amplitude all right, of a, you can say of a stationary wave, okay? All right, or all right, or a standing wave. So of a standing wave or a stationary wave, that is the maximum amplitude or maximum displacement. All right, so let's say of a standing wave. All right. All right. Also, just to make a point of this is that the antinode is also halfway between two nodes. Okay, so it is halfway. Let's say halfway between two nodes. Okay, very important to note that. So, and let's now talk about what a node is. Say a node now, so while a node is the minimum, so this will be the minimum. So while a node is, the minimum, the minimum point, all right, or displacement, minimum point or displacement of a standing wave. What is also important, you can also state this as well. This is when displacement is equal to 0. Okay, so here now, this is when displacement, or you can say displacement or amplitude, displacement or amplitude is 0. All right, so that's the difference there. So the maximum point is the antinode, and the minimum point or the minimum displacement, or where amplitude is 0, it is the node. So if I draw a wave like this, so let's do it real quick. All right, so let's draw a wave like that. All right, so let's ignore those bad things. So here will be our antinode. This maximum point here is the antinode. Just put a line right there. And these that I'm going to put, let's put in a different color, a point in different color, will be our nodes. So these here, all of these points will be our nodes. So notice they're on the 0 line with 0 displacement. Those are our nodes, and the maximum point, they will be our antinodes. All right, so let's go into the next part of the question. And this part of the question state the number of antinodes shown on figure 3. So based on this graph, or one of them, matter of fact, let's say this is one here and this is another one here. All right, so this for one of these wave or standing wave, then what you get here is 2 antinodes. Okay, all right, so you have 2 antinodes here. So this will be 2 antinodes. All right, based on the diagram, be a total of 4 in terms of the entire wave movement, but a single wave here going to be 2. Okay, all right, so going to be 2 here. All right, so just point that out. All right, for part C of this, the table 2 shows how the wavelength produced on a stretched string changes as the wave speed is varied. And so here, if you notice the trend for the speed, it increases by 5 and the wavelength increases by 0.06. All right, so if you notice the pattern with numbers, and then let's see what they ask us to do here. So on the grid provided in figure 4, page 11, plot a suitable graph to present the data. And so let's skip and go to the draw the graph that I've drawn before. All right, so let's just quickly go into it. And so the graph will look like this. Again, what I want to point out, because I know you need to do, I know you know to do this, but just to remind you real quick, is to make sure you put your scale. Very important. So use a scale and make sure you use large graphs, at least half of your page. And please label axis as well. Label all the axis. And also use straight fine lines. All right, you're not going to make your raggedy as mine. You're going to use your ruler to make a line nice and straight and smooth. And also your point's supposed to be fine, and indicate those points as well. All right, and so again, you label all the axes. All right, so now go back to the question. Let's see what they ask about the graph here. And here it asks us to determine the frequency of the standing wave. All right, so there are 2 ways that you can calculate this. And what I want to point out real quick is that when you talk about, if you want to find frequency, let's just give you a formula first, right? Say speed is equal to frequency times wavelength. Okay, if you remember that, okay? So speed is equal to frequency multiplied by wavelength. All right, and so if you want to find the frequency, then it's going to be speed divided by wavelength. So I must actually draw that in. So the frequency would equal to the speed over the wavelength. All right, and so if you go to the graph, you can use the longest point. So what I'm going to do here is to calculate the change in wavelength. And so what I'm going to use is my longest point. The matter of fact, you can use a graph. Let's say if they say use a graph, just to make sure. Okay, all right, they didn't say use a graph. Okay, so I'm going to use both the graph and also these numbers. So my wavelength starts from 0.6 because this increase uniformly and ends at 0.48. And so what I'm going to do is to find the difference between these 2 numbers. And I start here for my speed, it is 0.5 and it ends at 40. Why I'm doing this is to make sure I include all the points or as much points in my calculation, just in case you have any variation or any differences within these numbers, it will account for that. All right, so luckily the numbers are equal as well. So again, it is going to be 0.48 minus 0.06 and 40 minus 5. All right, and so the calculation here will be for the, let's just do that real quick. So it'll be 40. So 1 point will be 40. Let's put it here. All right, so 40. All right, I think I can put it right here. So 40 minus the 5, which equals to 35. And then I'm going to do the 0.48 minus the lowest point was 0.06. And what I get here is 0.42. Again, you put this now in the formula to say frequency is equal to 35 over 0.4. So let's just put that in real quick. So it's going to be frequency going to equal to here 35 divided by 0.42, and that will equal to 83.33 hertz. All right, or I could say per second. Now, another way you could do this is use the graph. But let me go to the graph to show you what you can do with the graph to find this as well. Now, you can use the gradient of the graph to find this. And what I want to point out, on the y-axis, you have the wavelength, but on the x-axis, you have the speed. So the frequency will be the inverse of the gradient. So you can make a note of that. So you can find the gradient, and as the inverse of the gradient will give you the frequency. All right, so in other words, 1 divided by the gradient will equal the frequency. All right, because y, because if you look at the change of y or change in x, it will be wavelength over speed, but you should have speed over wavelength instead. So again, it could simply be the 1 divided by the gradient, or you can say the inverse of the gradient. Okay, and the reason why I said that, again, let's go back to the equation, because here in terms of the formula that we use is that frequency is equal to speed over wavelength, but the gradient will give you wavelength over the speed. All right, so the inverse of it will be frequency. All right, so at this point I'm going to end, and this is only question 1 and question 2. I'll see how quickly I will come back and do the other questions. All right, so I'll catch you up real soon.